I'm Jung-Suk Park, and I'll be explaining the details of our research, mGEMM, low-latency convolution with minimal memory overhead, optimized for mobile devices. This research was done with my lab member, Kyungmin Bin, under the supervision of my advisor, Kyung-Han Lee. The convolution operation in mobile is used in many applications for tasks such as classifications, facial recognitions, or object detections. As can be seen from this graph, a large portion of modal latency consists of the convolution operation regardless of the network used. However, we still feel that many of these applications are still somewhat slow and unresponsive. As can be seen from these values, the convolution-based services in mobile are still quite slow despite the advancements such as mobile-centric networks, such as mobile nets, or optimization techniques such as quantizations. We searched for other venues of improvement and have found that the computation algorithms used for convolution computations in mobile are taken directly from that of the high-performance systems. This solution is based on GEMM, or general matrix multiplication. This solution is, like I said, taken directly from the high-performance systems. And while the GEMM computation itself is highly optimized in the mobile environment by the likes of Google and ARM, the approach of using GEMM in the mobile environment is highly inefficient due to the unique characteristics of the mobile environment different from the high-performance system. Unfortunately, however, the current solutions uses the copied solution from the high-performance systems without the regards to these differences. Our solution, mGEMM, solves this problem through three main contributions. The first, we analyze the current computation in mobile and find the reasons behind those problems. We then create a highly optimized convolution solutions for mobile based on this analysis and overcome the problems of the existing solutions and achieve higher low latency, minimal memory overhead, and optimizations for the mobile hardware. Finally, we create a real-world implementation of the mGEMM algorithm and test it on various off-the-shelf mobile devices to test our claims and provide a reference for future researches. Now, before diving into the details of our solution, we first provide you with some background on convolution computation. The convolution operation, or to be more specific, the 2D convolution operation, operates by scanning a small filter across the input and storing the output as another image. The filtering part is done by taking an inner product between the filter elements and the input sub-image that the filter is placed on. The result of the inner product computation is then stored as the output element. The current computation solution for 2D convolutions is by mapping it into GEMM, or general matrix multiplication. There were other solutions, such as FFT-based ones or vinegar transformation-based ones, but as these solutions lacked in generality, they gradually phased out, and the GEMM-based solutions became the de facto standard in convolution computations in all platforms, including mobile. The GEMM-based solutions operates by first flattening the input and filter elements into a column and row vector of two separate matrices. This transforms the inner product computations of the output elements into a matrix multiplication operation between the input and filter matrices. This mapping process is called image to column, and this allows the computation of 2D convolution using high-performance BLAS, or basic linear algebra subprogram libraries, provided in many platforms, including mobile, by the likes of ARM. However, this approach of mapping tensors into matrices requires the reordering of data into matrices, and also duplication of data for correct computation. This causes overhead and also increases the memory footprint, which ultimately leads to slower computation. Slower computation due to the increased number of memory accesses per computation. In the server or workstation environment, this is less of an issue as tasks in these environments, such as training networks or batch inference servers, are often supplied with large number of inputs. This allows the amortization of overheads and also increases the data reuse through the sheer number of repeated computation. This allows the GEMM-based solution to achieve high computational saturation and is also well supported by the powerful hardware that is capable of handling such large computations at once. However, in mobile, tasks are latency focused. This means that the users want the fastest and the quickest responses to their requests and only supplies one or few inputs at most. This renders the current GEMM-based solutions strategy of overshadowing the problems with sheer number of computations to be impossible in the mobile environment. This exposes the problems of GEMM solution directly in mobile, and which causes the convolution computations in mobile to be slower than what actually can be achieved in the mobile devices. Therefore, the need of mobile-centered convolution solution is necessary. This solution must overcome the problems of existing solutions and achieve high computational saturation even with low number of inputs provided. To do this, we first analyze the computation of convolution and GEMM. We provide you with the concept of computation space, which is a space where each point in the space is a separate operation that is required for the complete computation of the given computation. For example, in the graphics, we can observe that the matrix multiplication operation between the matrix A, B, C can be presented as a 3D space. The point I, j, k in this space can be understood as a multiply, accumulate, or MAC computations between matrix A element ik and matrix B element kj accumulated to matrix C element ij. Now, the computation algorithm can be understood as how the points in this space are traversed over. The same can be done for 2D convolutions as well. The detailed derivation steps are presented in our paper, but basically what we do is to map the dimensions of the 2D convolutions into that of the GEMM. This is possible for all dimensions except for the height of the filter and the width of the filter, or H-fill and W-fill. H-fill and W-fill dimensions cannot be mapped into any of M and K dimensions as they require, as the traversal over this H-fill and W-fill dimensions accesses the same tensor data for both of the input and output, which is a trait that none of the M and K dimensions have. And therefore, they must be presented as a separate dimension as shown in the graphics. This causes the final computation space of the 2D convolution to be represented as a 5-dimensional space. Now, the current computation of mapping convolutions into GEMM can be understood as slicing this 5-dimensional space along the H-fill and W-fill dimensions to create 3D subspaces. These 3D subspaces then can be stacked on top of each other to create a flattened 3D version of the original 5-dimensional space. Now, this 3D space can be computed using GEMM and high-performance BLAS libraries. Unfortunately, however, as each 3D subspaces share the same output and input data, stacking them on top of each other causes either the input or output data to be reordered and duplicated, causing the problems we saw before. Therefore, the cause of the problems of the existing solutions can be understood as coming from trying to map a 5D space into a smaller 3D space of GEMM. Our approach is to reverse this concept and expand the computation space of GEMM into that of the convolution operation by adding computations of H field and W field between the iterations of k dimension of GEMM, allowing the reuse of output and input data loaded on the registers between these iterations. This allows us to remove the need of duplication and reordering, solving the problems and achieving higher computational saturation without the need of large number of inputs. Of course, this isn't the only thing that makes our solution special. We studied many papers about GEMM algorithms to learn their secrets about algorithmic structures, hardware accelerations, and optimization techniques. We took these techniques and modified them to fit the nature of the mobile environment and applied it on our final mGEMM algorithm. The detailed derivation steps for our final algorithm can be found in our paper. To test our final mGEMM algorithm, we present you with YOLO version 3 tiny object detection results of mGEMM on 3 different mobile hardware compared against the state-of-the-art solutions from likes of Google and ARM. ARM-NN is from ARM and XNFPEG is from Google. From the graph, we can see that mGEMM is able to achieve the best performances in all dimensions, even when compared to the state-of-the-art solutions from Google and ARM. This shows that our approach of tackling the problem from a mobile-centric perspective is crucial when compared to the existing solutions which took their solutions directly from that of the high-performance systems. The similar results are found in other devices as well. This shows that the benefits of mGEMM is device-independent, and mGEMM is the right step in the right direction for convolution computations in mobile. The takeaways from our research can be boiled down to 3 main points. The first one is that the current convolution solutions in mobile are not mobile-focused and are directly copied from the high-performance systems. This indicated a huge opportunity for possible improvements which our research focused on. The second would be that the computation can be analyzed to reveal the core difference and the reasons behind the problems. This acted as a major hint and a guideline when we are creating our highly optimized solution. Finally, the algorithmic improvements of our mGEMM solution offers large benefits regardless of the dimension and regardless of the hardware. This is because our solution is an algorithmic improvement and not a trade-off. The future works for mGEMM might consider something like GPU implementations of mGEMM or expanding the mGEMM algorithm for mobile network training. But we'd also like to mention other venues of algorithmic improvements in mobile, such as heterogeneous systems or computational offloading or IoT clusters. We have applied our approach of algorithmic analysis and computational improvement on some of these venues and was able to yield some very intriguing results. We believe that computation and algorithmic improvements can be a great benefit for the mobile system. We hope to see the improvements for computation and algorithm more from the mobile systems. But for now, this is the end of my presentation. Thank you for listening. I'm Jung-Suk Park.